Good morning, students. Today we will discuss the expansion of a symmetric kernel in terms of its eigenvalues and eigenfunctions. This kind of expansion of the kernel in terms of eigenvalues and eigenfunctions, that is also called bilinear form. So in order to derive the bilinear form, let us take a kernel K which is non-null symmetric kernel, and suppose this kernel has finite or infinite number of eigenvalues. Let those eigenvalues are lambda 1, lambda 2 and so on. As we already discussed, the eigenvalues of symmetric kernel are always real. So all these eigenvalues, lambda 1, lambda 2, lambda 3 and so on, these eigenvalues will be real. And also these are non-zero eigenvalues. Now let us arrange these eigenvalues in the order that corresponds to their absolute value. It means we have taken 0 greater than lambda 1 mod, less than or equal to lambda 2 mod and so on. We have arranged them according to their absolute value. Now let us take the corresponding eigenfunctions phi 1, phi 2, phi 3. These are the corresponding eigenfunctions, and these eigenfunctions are also arranged in the form that these are no longer repeated. Also these eigenfunctions, because they are distinct and therefore they will be linearly independent eigenfunctions. Now as we discussed already in Gram-Schmidt procedure, that a linearly independent set of functions can be converted into an orthonormal set. So we can normalize these linearly independent eigenfunctions. Now let us take lambda 1 is an eigenvalue for the symmetric square integrable kernel, and let us take phi 1 with a corresponding eigenfunction. Now let us define the truncated kernels which will be used in this form. The second truncated kernel, that is defined by the difference of the kernel KST with phi 1 into phi 1 conjugate divided by lambda 1. This difference, that is called the second truncated kernel. So this kernel is also non-null kernel, and this will also have an eigenvalue. So let us take lambda 2 with the eigenvalue of this kernel, and the corresponding eigenfunction is phi 2. This phi 1 and phi 2, these two functions, they will be different functions. Similarly, we can define the third truncated kernel, which is defined by KST minus phi 1 into phi 1 conjugate divided by lambda 1 minus phi 2 into phi 2 conjugate divided by lambda 2. This is third truncated kernel. This kernel will also have an eigenvalue, and the corresponding eigenfunction we have denoted by phi 3. Continuing like this, we can define the n plus 1th truncated kernel, which will be given by kn plus 1 st is equal to kst minus summation I varies from 1 to n phi I into phi I conjugate divided by lambda I. Now we will have two possibilities. Either this process will terminate after n steps, or we will have an infinite sequence of eigenvalues and eigenfunctions if the process continues indefinitely. So if the process terminates after n steps, means n plus 1th truncated kernel is 0. So in that case, we have kst minus summation I varies from 1 to n phi I into phi I conjugate divided by lambda I is equal to 0. So from here we get the value of the kernel in terms of eigenvalues and eigenfunctions, which is given by kst is equal to summation I varies from 1 to n phi is into phi I conjugate divided by lambda I. So this kind of expansion of the symmetric kernel K, that is called bilinear form. In the another case, if the process continues indefinitely, in that case we have infinite number of eigenvalues and corresponding eigenfunctions. So this was how can we expand a symmetric kernel in terms of eigenvalues and eigenfunctions. Now next we discuss some theorems based on the symmetric kernels. So the first theorem is, if we are given a symmetric square integrable kernel KST and lambda k is the sequence of eigenvalues and phi ks be the sequence of all the eigenfunctions, then we are to prove that series summation n varies from 1 to infinity phi n mod square divided by lambda n square that converges, and the sum of this series is bounded by C1 square. Here C1 square is the upper bound of the integral KST mod square. So in order to prove this, firstly let us define the Fourier coefficients of the symmetric kernel K with respect to an orthonormal system of functions. So let us take, because we are given phi k are the eigenfunctions of the symmetric kernel, because by Gram-Schmidt procedure they can be normalized. It means that system can be converted into orthonormal system, and the corresponding conjugate system of an orthonormal system that is also orthonormal. So we can say phi k conjugates, they also forms an orthonormal system. Now let us take an be the Fourier coefficients of the symmetric kernel K with respect to this orthonormal system. Now by definition, Fourier coefficients AK for the kernel K are given by the inner product of the kernel with the members of orthonormal system. Now by definition of inner product, this is given by integral K st into the conjugate of these functions. The conjugate of phi k star, that is phi k. Now multiplying and dividing by lambda k, we get now this quantity, because lambda k is eigenvalue and phi k's are corresponding eigenfunctions for the symmetric kernels. Therefore the symmetric integral equation that will be satisfied. So in this equation lambda is replaced by lambda k and the function g that is replaced by phi k. So in that case here we will get phi ks. So we have substituted the value here, which is phi k divided by lambda k. So we have obtained the values of the Fourier coefficients. Now let us use Bessel's inequality. So according to Bessel's inequality, if ai's are the Fourier coefficients, then summation ai mod square is less than or equal to kst norm square. Now substituting the values of the Fourier coefficients which we already obtained in the last step, the value of Fourier coefficient ai is phi is divided by lambda I. So here we have substituted the value of Fourier coefficients on the right side using the definition of norm. By definition, norm is given by the square root of inner product of the function with itself. So kst norm square means inner product of the function kst with itself. Now by using the definition of inner product is given by the integral of the product of first function with a conjugate of second function. So we have summation I varies from 1 to infinity phi I mod square divided by lambda I square is less than or equal to integral kst mod square. Now because we are given an upper bound for this integral which is c1 square, therefore this integral will be less than or equal to c1 square. So from here we have obtained that the series which is given by summation I varies from 1 to infinity phi I mod square divided by lambda I square, that is less than or equal to C1 square. Thus we can say that the sum of this series is bounded by C1 square. Also, this series is a positive term series and that is also bounded, and therefore this series is convergent also. So this proves the theorem based on the symmetric kernels.